All right, so thank you everyone to join this CS seminar. So it's my great pleasure to introduce Kexin Pei. So he's a fifth-year PhD student at the Department of Computer Science of Columbia University, and he's co-advised by Dr. Suman Jana, Dr. Junfeng Yang, and also work closely with Dr. Benshikash Ray. His research interests broadly lies in security, systems, machine learning, and also especially with a focus on developing machine learning architectures to understand program semantics and using them for program analysis and security. So it's kind of like a joint of machine learning and program analysis. So it's a very trading topic this year. So with that said, so he's going to present a talk on scalable, accurate, robust binary analysis with transfer learning trace modeling. So let's welcome him. So yeah, please, it's yours.
Thanks for the introduction, Inge. Hi everyone, I'm Kexin Pei, and it's my great honor to present here. And I really hope to learn more from also you guys on my recent project. So today I'm gonna present my recent two papers on binary analysis called Scalable, Accurate, Robust Binary Analysis with Transfer Learning, Trace Modeling. And this paper is done with my wonderful collaborators as well as my advisors. Let me start now. So binary program analysis consists of many fundamental subtasks that aim to analyze programs at the binary level. And it has many security critical applications like vulnerability detection by fuzzing binary programs directly, or security retrofitting such as retrofitting control flow integrity or malware analysis, and so on and so forth. Binary analysis is a process of understand, analyze, and answer questions regarding binary program behavior, usually partial program behavior. For example, if you are doing binary similarity, you are essentially asking whether two binaries compiled to different architectures by different optimization flags can perform similarly during runtime. And if you're performing vulnerability detection, you're essentially asking whether the variable can overflow during runtime. And if you're retrofitting security control flow integrity, you're essentially asking whether certain function can call another function during runtime, for example, via indirect calls. And in order to answer these questions, there are many intermediate tasks that aim to recover program properties and dependencies, such as disassembly and recovering function boundaries, also like doing type inference, and also recovering control and data dependencies. However, binary analysis is fundamentally challenging. This is because symbol information such as types and variables are lost in the compilation and compiled down to untyped registers and memory accesses. The task gets exacerbated as the binary can be compiled by different compilers, optimizations, and obfuscations, and running on different operating systems and architectures. If we look at the existing binary analysis solution, the typical design approaches the problem as a pipeline of design. For example, the very first step of binary analysis is often disassemble the raw binaries into assembly code, perform some basic type inference of registers and memory accesses. Then it recognizes higher level constructs, such as functions or basic blocks, and derive more complex dependencies, such as points to analysis to infer memory dependencies, control and data flow dependencies. And all these recovered properties and dependencies enables more advanced downstream tasks, such as binary program slicing, taint analysis, symbolic execution, abstract interpretation, which further facilitates many security applications, such as fuzzing, verification, hardening, debloating, etc. Oftentimes, we observe that these tasks are not strictly forward dependent following this order. For example, in recursive disassembly, such as IDA-Pro and Ghidra, it follows the program control flow and only disassemble the functions that are reachable in the control flow graph. Indirectly reachable functions are not disassembled. Also, some type inference works require propagating variable types through instructions that involve memory operations. Tracking memory dependencies can help the type propagation of variables that get stored in the memory. In addition, in order to infer memory dependencies, some advanced program analysis tasks, such as value set analysis, is often used, and it is based on abstract interpretation. In the end, these binary analysis tasks become largely interdependent, like a spaghetti. However, the inaccuracy in one task can get amplified too. In addition, we also observe that all these binary analysis tasks share some common basis. Just like any program analysis task, they all aim to understand partial program behavior or semantics from different perspectives. For example, if you're doing type inference, you are essentially asking how register or memory should be manipulated in the runtime. If you are doing memory dependence, you're essentially asking what memory addresses will be accessed in the runtime. The knowledge in one task, however, we observe that existing works often design ad hoc and isolated heuristics for each individual task, ignoring such a common basis. So the knowledge in one task is not generalizable to another task, which is also the reason why those heuristics are brittle, as they do not capture the underlying inherent program behavior. Finally, we noticed that a lot of existing tools rely on manually constructing heuristics by domain expert. This database of patterns need constant maintaining and update. For example, both IDA and Ghidra maintains a large pattern database and needs to cater to new compiler idioms or new architecture specifications frequently. Recently, machine learning approach has shown many promising evidences for binary analysis. It partially addresses some challenges as mentioned in the previous slides. For example, it is often automated based on the data-driven approach, alleviating the manual effort in designing heuristics. And it is efficient as it can often accelerated by GPU if we are using neural network. It has achieved significant successes in understanding, analyzing, and generating many programs, including source code. If you notice, recent OpenAI and GitHub released this GitHub Copilot. By training only on the natural language comments along with the source code script from GitHub, it can generate the source code by simply giving a natural language prompt. And it helps the programmer a lot recently. However, we observe that existing machine learning-based binary analysis approaches still have many limits. As shown in the figure, typical modeling practice of machine learning is to treat each binary analysis task as individual training objective. It designs training algorithms, loss functions, and model architectures that are tailor-made to each task. However, such a setting ignores the common ground of or shared knowledge between these tasks. All of them essentially try to learn partial program operational semantics. We find that with such a setting, the model often overfits to individual tasks, learning task-specific spurious correlation. Even when it is learning generalizable program operational semantics, it wastes effort by learning some knowledge over and over again. Our key insight is that in order to understand program operational semantics, the model usually needs to observe how program executes and can imagine how program would behave during runtime by looking at the static code. However, the common assumption of all existing data-driven program analysis approaches, even including that of recent Copilot powered by GPT-3 Codex, is that code, just like natural language, exhibits naturalness and certain facts about the program can be learned from large code samples by treating them as some form of natural language. Therefore, existing works often treat programs as plain texts or more advanced structured inputs like trees or graphs. However, the key problem of this assumption is that program code, unlike natural language, needs to be executed. Its semantics is inherently manifested in its execution traces. Therefore, it makes sense in natural language to use this kind of word-to-vec style embedding that leverages local context to learn the semantics. For example, here the meaning of banana and orange is determined by their shared context, fruit. However, if you look at the program code, the code token semantics is usually not implied by its neighboring context. For example, here the semantic is move cannot be determined by the name of its operands. Instead, we should observe the execution effect of move based on its traces in order to determine the semantics of move indicates moving the value from its second operand to the first operand. So our key idea is to first teach the machine learning model to observe and understand how program behaves by training it on both the binary code and its execution traces. Then we transfer the learned knowledge of program operational semantics to perform different downstream binary analysis tasks. Specifically, given a huge set of binary code collected in the wild, we leverage the chip emulator to generate its approximate execution traces. Then we train a neural network to serve as a program interpreter and synthesizer by forcing it to predict the execution traces given the instructions, or synthesize the instructions given its execution traces. In order to minimize the prediction losses on such a wide spectrum of programs and trace values, the model is forced to understand the actual meaning of different static code and learn to reason about the program behavior. We found that such knowledge learned from this pre-training task is extremely helpful. It is agnostic to downstream analysis tasks, so it does not overfit to shallow task-specific features. It is also a very challenging task, and it forced the model to learn deep and generalizable knowledge, as the model cannot easily memorize billions of samples or learning easy shortcuts. We also find such knowledge is extremely transferable to many program analysis tasks, which is intuitive as we described earlier. All of them benefit from the understanding of program behaviors. Finally, our pre-training task leverages this popular idea of self-supervised learning. Therefore, it does not require manual effort to collect ground truth. After the model is pre-trained with trace modeling, we transfer its knowledge by fine-tuning on various binary analysis tasks based on a limited labeled samples. This time, we do not execute the code at all. Instead, we simply let the model take the complete static code as input and try to imagine its potential behavior based on its understanding of its execution behavior semantics, and then transfer the knowledge of such an understanding to perform specific binary analysis tasks. Turns out that such setting is extremely lightweight, as it is static analysis powered by neural networks with GPU. In the following, I will elaborate the idea of transfer learning trace modeling in two instances that we implement to solve two binary analysis tasks, which are matching semantically similar binaries and binary type inference. First, let me start with the first paper, Tracks. Tracks handles binary code similarity task, and the binary code similarity has many security applications. For example, if you want to do vulnerability detection, you can use a vulnerable function as a query and search in a large set of firmware images and find similar code which has similar vulnerability. Or you can do malware analysis, try to find the similar malware family of a new malware variants. And it also helps with reverse engineering and forensics. And traditional approaches for identifying semantically similar binaries often suffers from the following limitations. For static analysis, they usually extract some signatures by domain expert and match the signature between different function binaries. And this kind of approach often results in high false positive and negative because the defined signature is often not complete, and it is hard to adapt to the new compiler idioms. And more advanced approach leverages dynamic analysis, which tries to execute the program code and match their dynamic behavior to determine whether they are similar or not. However, this kind of dynamic approach often suffers from low coverage as well as large runtime overhead. If you're gonna compare millions pairs of function binaries, you have to execute each pair every time when you try to compare. And deep learning based approaches have shown promises in recent literatures. They are, first of all, data driven. So they have saved substantial manual effort by learning representations automatically. They're also extremely efficient because the learned representation are often just an embedding, which is a vector representation, and matching many vectors by computing their similarity is super fast, like using approximate nearest neighbor. However, as I have discussed before, they all assume programs as plain or structured text code without really understanding the program's execution behavior. For example, as shown in these two code pieces, they are both setting EAX to 0 and then try to increment EAX by 1. They have exactly same behavior or exact same semantics. However, they have very different syntactic texts. So without understanding the actual execution semantics of move, XOR, or other operations, ML algorithms often pick spurious correlation to learn that these two code pieces are similar. Here are some examples why understanding binary program execution semantics is important. The first example is in the first row illustrates two binary functions compiled from the same exact implementation, but to different architectures. Both functions are comparing the lower 12-bit of a register to a constant. On the left-hand side, x86 binary implements this using a logic AND, while ARM binary makes use of a combination of shift left and shift right. Due to different syntax between x86 and ARM, and even this different implementation, two binary code are not similar, but they share the same functionality. The second example shows two code pieces extracted from the same core utils functions, but compiled by different compiler optimizations. Both share the same semantics by reading the function's first argument, but we can see that the function prolog that saves the base pointer on stack is optimized away when compiled in O3. The third example shows two code pieces still coming from the same function in OpenSSL, but get obfuscated with LLVM obfuscator with instruction substitution, while both code increments EAX by 1. Unlike the straightforward implementation from the original code, the obfuscated code first sets ECX to 0, minus it by 1, resulting in -1 in ECX, and then subtract EAX by ECX, which is -1, which will have the same effect as +1. All this example show that if we are gonna match the similar binaries without dynamic execution, without really understanding that the execution semantics of XOR and shift left, etc., the model cannot deduce the approximate effect of the executing the code, thus resorting to other superficial textual features. Therefore, learning only on static code does not really help the model learn code semantics and use that to match similarity. The key idea of tracks, as described previously, is to first pre-train a neural network on a large number of binary code and their execution traces to observe the execution effect of each instruction and their combination. Then we transfer such knowledge by fine-tuning the pre-trained model to encode the actual binary code into embeddings and match the similarity between their embedding vectors. To collect execution traces of diverse binary code blocks, we leverage micro-execution to execute each function multiple times. The basic idea is to initialize all registers with random values, except special purpose registers, such as stack pointer and program counter. And then we leverage the idea of forced execution, which skip unreachable jumps and calls, and helps the model to keep executing the function till the end of the function and exposes more behaviors. Therefore, while this introduces more under-constrained execution traces, we find it to be beneficial for obtaining more diverse instructions for pre-training. Moreover, since we pre-train over a substantial number of functions, our insight is that a certain instruction not micro-executed in one function is highly likely to appear in at least one of the other functions in the microtraces. Note that tracks mask, we leverage the mask language modeling in tracks, and this masking strategy helps it to learn embeddings at the instruction level. Therefore, it enables the model to learn the composite effect of the instruction sequences, so it can generalize to unseen combinations of instructions. Let's look at the architecture of tracks in more detail. The input of tracks consists of both the tokens from instructions and traces aligned together. Besides the two sequences, we also stack instruction positions, the OP code operand positions within each instruction, and architecture sequences denoting the target architecture on which the binary code runs. The first two sequences encode the two modalities of the code piece, representing the static code and its execution traces, which represent its execution behavior, while the remaining sequences provide auxiliary annotations. Then, given this input, we first embed each token from each sequence and aggregate them with a vector summation operation. Then we leverage the self-attention layers from transformer to learn interactions between instructions and their execution traces. In order to force the model to reason about program execution behavior, we design the training objective that asks the model to predict random masked trace values as well as the code values. For example, here we try to mask the add token in the instruction sequence and ask the model to predict what is the masked value in the instruction sequence. We can also mask the value in trace value sequence and ask the model, given the unmasked code sequence and the trace values, what would be the masked trace value here? And the intuition of the trace modeling here is shown as follows. The first example here, we just try to mask the value of ECX equals to 1 here. And this actually forces the model to perform the forward reasoning to deduce what is the value after seeing 2, seeing subtraction, and 1. And this helps the model to understand, in order to predict the value, the mask value here to be 1, this helps the model to understand the operational semantics of sub-instruction. And also here, if we mask the previous value of 2, and this also forces the model to understand the operational semantics of subtraction by performing this backward reasoning. And here, if we mask the token in the instruction sequence, which is addition, we're asking the model to perform this inverse reasoning by performing program induction, which is given the input and output, 1, 3, and 4 here, the model has to understand the operational semantics of addition in order to predict here the token should be addition instead of subtraction or XOR or other tokens. And turns out that the deduction, abduction, and induction during this mask language modeling process is an irreducible set of reasoning primitives in human brain, and predicting multiple mask tokens in both instruction sequences and trace values force the model to understand diverse instruction semantics and also reason about their compositions. Also, when we try to encode the actual value in the value sequence, we find that the vocabulary size for learning value trace embeddings is prohibitively large. For example, on a 64-bit architecture, there are 2 to the 64 number of possible values, which makes our encoding mechanism cannot simply work. What we perform here is that we first try to replace all the numerical value appeared in the instruction sequence to be a dummy value called num, and then we move all the actual value sequence to the trace value sequence. And in order to encode the trace value sequence that have 2 to the 64 potential values, we break each value further into 8 bytes, which forms a sequence. And then we use the LSTM to aggregate this 8 bytes as a simple representation of that number. And this effectively reduced the 2 to the 64 number of vocabulary to only 256 number of possible bytes. And also using LSTM can capture their relative position, which can encode the relative significance of each byte in the 8-byte encoding. And here, given after pre-train the model with trace modeling, what we perform here is try to take 2 binary code pieces that we want to detect whether they are similar or not, and try to encode them using the static trace without any execution traces. Here, the execution traces becomes then dummy, which makes the binary similarity comparison become static. And then we try to maximize the agreement between similar function code and try to minimize the agreement between dissimilar function embeddings. And here, note that we no longer micro-execute the code. We only feed the static code to the pre-trained model and ask the model to transfer its learned knowledge of the instructions to infer whether the 2 functions are similar or not. This makes our comparison algorithm to be extremely efficient. What we can do is we simply feed a large-scale binary functions, compute their embeddings, and match their embeddings using approximate nearest neighbor algorithm. We collect extensive data set to evaluate tracks from different architectures, compiler optimizations, and obfuscations. And we compare tracks to 4 state-of-the-art baselines using machine learning and traditional dynamic analysis. And as the cosine similarity between 2 function embeddings can be arbitrary real value between -1 and +1, there has to be mechanism to threshold the similarity score to determine whether the function pairs are similar or dissimilar. To avoid the potential bias introduced by a specific chosen threshold value, we consider the receiver operating characteristics, which is the ROC curve, which measures the model's false positives and true positives under different thresholds. Notably, we use the area under curve of the ROC curve to quantify the accuracy of tracks to facilitate benchmarking. The higher the AUC score, the better the model's accuracy. And as shown in here, we can observe that tracks performs consistently well, even on the architecture, on the binaries can compiled from different architectures, different optimizations, and different obfuscations. And it is only 0.035 lower than when we compare the functions from the same different architecture, but on the same optimization and obfuscation. And when compared to the baselines, we find that tracks outperforms existing state-of-the-art machine learning-based models, which learns only on the static code. And it also outperforms the traditional dynamic analysis approach. And we also do ablation studies to try to evaluate the effectiveness of pre-training by learning execution semantics on both static code and traces. We find that without pre-training, the model achieves 15.7% lower AUC score than pre-training. And we also find that by pre-training only on a very tiny number of execution traces, like 30%, the model also achieves very good accuracy. In summary, we find that tracks outperforms the state-of-the-art in matching functions from different instruction architectures, different compiler optimizations, and different obfuscations. And it remains accurate and robust across binaries from different idiom syntax and semantics. Do you have any questions for now?
Yeah, maybe I can ask a quick question. You mainly use, I like the intuition there about like masking certain part of like operators and also like certain registers. So this is more about like a data flow information. So it's being masked, especially the traces about data flow. So how about like control flow information, especially, for example, consider we have a ROP based like a return-oriented programming. Another is maybe normal programming. So the difference is actually lies in the control flow, right? So the ROP is really based on how the different returns happens, and the normal is based on if statement. So if those two code are similar, one is using ROP, another is using like a normal programming. So can you like also like identify similarity between these two types of code?
Right, that's a great question. We indeed consider that before, but we find that in matching code similarity, the control flow of the code does not matter that much when doing pre-training. So that's why in pre-training, when we micro-execute the code, we kind of not respect the control flow by plain execute the function, ignoring its jumps and calls. And that's why this creates an under constraint and approximate execution effect of the code, which only helps the model to learn execution effect of individual instructions and their simple combinations. But for difficult downstream analysis tasks like type inference that I will describe later, like you said, the control flow becomes very important. That's why in the micro execution trace collection, we did collect the control flow information and also force the model to predict not only the data flow, but also the control flow. So it turns out that that modeling helps the model to learn for more difficult downstream analysis tasks. But for binary similarity, yes, we find that, yeah, learning control flow does not improve the model that much. Thanks for the question. Yeah. Okay, so now I will just jump quickly to the second work, and it also leverages similar idea of trace modeling, but with several improvements over the previous pre-training in tracks. And this paper is about type inference on binaries using this trace modeling idea. And as still some background, type inference on binary is a process of recovering source level constructs, such as primitive variable types and the member fields types from the strip binary. And it is also a fundamental binary analysis capability useful for many security applications. For example, in security retrofitting, we need to retrofit control flow integrity. This requires reconstructing call graph, as indirect calls at binary level often complicates the problem. Existing techniques often resort to type inference to predict the function signatures of both the call site and callee. If the types match, we know that the call may reach bar. Here, the full may reach bar. If they don't match, we know for sure that the call cannot reach the callee. In postmortem vulnerability diagnosis, we also often have to pinpoint the error-inducing inputs by tracing back instructions from a core dump. This involves performing alias analysis to eliminate bloated instructions like slicing. For example, if the operand of one instruction may alias the output of another. So existing techniques perform type inference and prune the instructions when their memory accesses have different types. However, binary type inference, just like any other binary analysis tasks, are fundamentally challenging. This is because all source level data structures, variables, and arguments are lost and compiled down to untyped registers and memory accesses. The task also gets exacerbated as the binary can be compiled by different compilers optimizations on different operating systems and architectures. While there are many existing works on type inference, traditional approaches based on static and dynamic analysis are limited by low code coverage, large runtime overhead, and non-trivial manual effort. More recent approaches also show promises by using machine learning approaches to learn from code patterns. However, like we discussed before, learning only on static code does not capture its actual semantics. Therefore, it has been shown that often learning spurious shortcuts lacking robustness of these machine learning approaches. So in this paper, we aim to teach the ML model the required knowledge of human reverse engineer when performing type inference. So when thinking about how human analysts make sense of binaries, they often just look at the code and approximate its possible runtime behavior by reasoning the execution effect of each instruction in their mind. They like to ask what would be the approximate effect after executing certain instructions. Such a mental execution often requires the understanding of the operational semantics of each instruction. And it turns out that this mental execution model is the key factor that supports the analyst to infer types. In fact, types essentially specify at a high level how variables in the program are expected to be manipulated and accessed during runtime. For example, for arrays of integers, they are usually accessed sequentially with fixed sizes, and variable size accesses from the same base pointer usually indicate a struct variable or arguments on the stack. So here we still leverage the idea of trace modeling and transfer learning. We first also learn instructions and the trace values by forcing the model to learn how instructions produce the trace values. And then we transfer this learned knowledge for type inference. And here we, like what Inge asked, we also augment our pre-training task with learning control flow. And here we also we made a lot of improvements, like increasing the masking rate, as well as using the curriculum learning to help the model to gradually increase the learning difficulty. But I will just omit the details here and directly jump to the results due to the time. So we evaluate StateFormer on 33 popular open source software projects, and they are also compiled down to different instruction set architectures by 2 compilers, as well as 4 optimizations and 3 obfuscations. And we compare StateFormer to 3 state-of-the-art machine learning-based type inference tool. The first one, Eclavia, trains the neural network as RNN to recover function signatures, which includes the number of arguments as well as the argument type for each function. And Debian, which recovers variable name and the types from the binary, as well as type miner, which try to recover more fine-grained type information from the binary. And we evaluate all the benchmarks, all the baselines, and our tool using precision recall and F1 score. And the first main result from StateFormer is that we can observe StateFormer performs equally well on different instruction set architectures as well as different optimization levels, achieving 77.9 F1 score on average. And it outperforms Eclavia on function signature recovery by 13.3 and outperforms Debian 14.6 throughout all architectures and optimizations. In summary, we find that for both papers, program operational semantics is often used by a human analyzer to reason about program runtime behavior, which provides important type hint for binary type inference. And motivated by this observation, we propose this trace modeling to force the model to learn operational semantics of the code. And we find that it significantly boosts many downstream applications, including type inference and binary similarity. And we also released the code and data set here. Yep, that's all about my talk. Thanks so much.
Thank you, Kexin. Great talk. Like it a lot. So any question from the audience, please feel free to either type into the chat or you can just open your mic and speak now.
I have a question, if it's okay.
Go ahead.
Yeah, so yeah, very interesting talk. So transfer learning is kind of my area, so I'm very interested in this topic. I haven't really touched applications like in code analysis, binary analysis, so this is very cool things to learn about. I think I have questions on the spurious correlation. You mentioned a lot, right? But I feel this term is not well defined. It maybe mean different things in different areas. For example, in the image case, it's maybe the background is the spurious correlation you want to eliminate in your analysis. So I was wondering in this task, what's the spurious correlations definition, and also is there possibility to build a more causal model to reason about things, so we do not consist spurious correlation in your modeling?
Yeah, thanks for the question. Yeah, this is a very, very interesting question that I also care a lot about when applying similar idea popularized in machine learning to program analysis. Here we observe that by spurious correlation or spurious shortcuts learned by the model is simply common substring. For example, when you try to match the similar binaries, machine learning algorithms, without learning this execution semantics, they often use the common substring as an important feature, which seems to be very shallow, but since that is like heavily used to match similar binaries. And we also find that some robustness is lacking for this kind of static learning model, for example, by perturbing the tokens, like different registers, as well as their values. The model still predicts that 2 functions are similar. In fact, changing those critical registers or values will render 2 functions to be functionally very dissimilar. And we call this as spurious correlation. But yes, it might be very interesting to try to improve it using causal model, like you said, or or like clearly define what do we mean by spurious correlation. Yeah, thanks for the suggestion.
Yeah, I feel there's difference, right? So for example, in image case, if you perturb something and in the adversarial robustness case, you think you should keep the same result because that's the in the imaging scenario. But in this case, if you just manipulate something and it actually changes things a lot. So then, yeah, maybe, yeah, I feel there's interesting differences in these two areas, and yeah, definitely something to look more into. Yeah, thanks.
Yeah, this is very interesting. We are indeed exploring architecture that can preserve this equivariance or invariance, like you said. And yes, we have explored different architecture other than transformer that is more suitable for modeling code and traces. So yeah, we can talk offline. This is very interesting.
Yeah, thanks.
Sure.
Any other question from the audience? Maybe I can ask another question when people are thinking about their questions. So I know this is applicable to like binaries and compilers, but have you think about applying it to some like scripting languages, like goes through maybe like interpreters, and also sometimes may have like a just-in-time like a compilation being involved. Examples are like a PHP, like a Python, JavaScript. So I mean, they also have like, for example, opcode that's being involved. They have some intermediate languages. So is like a approach or techniques described here for like inference, for similarity comparison, also applicable in those areas? I mean, do you have any thought on that?
Yeah, this is a very, very nice question, and we are indeed collaborating with other people working on JavaScript by recording, their source code as well as their execution behavior. And I'm not that involved in that project, but as far as I know, the key challenge is that the language is much richer for the scripting language as well as source code than the assembly language, and also tracing their application, tracing the program will also have much more states corresponding to different variables or different memory than tracing assembly code. But the preliminary results, as far as I know, is still quite good for learning some source level vulnerability localization detection task, even using this kind of modeling. And we are also working on applying this idea in Java by incorporating not only source code and the trace value, we also try to incorporate the testing code for different Java programs. And turns out that by incorporating this different modalities of the program code really helps the model to learn many downstream applications on this program.
So may I ask, I'm not sure if you know, which JavaScript analyzer are you using like for your analysis? Because I'm asking because like our group have a JavaScript analyzer that is actually going to publish in this year USMIT. So it's the latest one. So
okay. Yeah, I am not so familiar with the tool underlying their implementation, but yeah, I can definitely connect you. I will ask them later and send you.
Okay, we can talk offline. Yeah.
Yeah.
With that said, any other question from the audience when we're talking here? Okay, still a little bit silent. So let me ask you another question then. I remember that in your analysis, you need to collect like this trace, you call it like a micro trace. So in order to collect trace, you need to have like input. So in order to trigger like different branches. So sometimes people have the very advanced filing technologies to really trigger the input. So in your case, like what type of like fuzzing or what type of analysis have you used to really output different values? Because it really depends on what user input to your program, and the different input leads to different result, based on your analysis.
Yeah, that's a great question. So that's why we make the tracing only happen at the pre-training level. So what we did is we leveraged micro traces which only produce under constrained execution traces by just randomly initialize registers that are involved in the execution, as well as the memory that will be read and write on the fly. So the execution is by no means close to the real execution of the whole program. And we do not use any fancy fuzzing technique to make the coverage high for executing functions. What we care about is we just want to collect a huge number of traces by using randomized initialization of registers in the memories, so that the model can observe as many execution behaviors as possible. So that's why in matching function similarity, we even ignore the control flow, like you asked. We simply execute the function up till the end, ignoring all external function calls as well as control flow jumps. And we find that this noisy traces does not affect the learned knowledge of pre-training that much. Indeed, if they are used in fine-tuning for matching similarity, they are very important. They should really reflect the model function behavior. But it turns out in pre-training, the model just learns some basic understanding of how program execute and then transfer for statically matching functions. And it turns out that are still useful. But definitely if micro executing the code with more advanced strategy can be a very interesting future direction.
Do you have a code coverage number by any chance? Like it's what level? Like maybe as high as like 90% or as low as like around like 30 or 50%?
Yeah, in state former we only have around 50% code coverage on average. Yeah. If we ignore the control flow jumps, it is like a virtually 100% coverage, but it does not mean anything.
I see. Okay, I've asked many questions. Anyone want to ask a question?
Yeah, I have a question. So I was curious when, going back to Trex, you have binary matching sort of tool here. Have you thought about applying this, or have you tried to apply this for vulnerability discovery or matching things that are, things like CWEs or common weakness enumerations that would be common across various codes? So perhaps, instead of using a signature to identify these, you use your learned behavior model.
Yeah, that's a very good question. And we do have apply it on searching large scale firmware image dataset. And what we used is we find a CVE of certain OpenSSL functions. And then we use that function compiled as x64 on our own machine and match them in firmware, which is usually compiled by ARM or compiled to ARM or MIPS using unknown optimization level. And turns out that the result is also very promising, and we outperform the existing baselines on this data set.
Awesome. Yeah, that's encouraging.
Thanks for the question.
Yeah.
Okay, any other questions from the audience? Okay, maybe I can ask the last question. If no other question, we can end. I know this is about like a transfer learning. So I didn't see much, maybe that's based on my understanding of transfer learning. So I didn't see much about transfer here. I thought it's like you transfer from like one domain to another domain like maybe you're training on image, but going on the like a language. And then the transfer usually happens like when you, like for example, freeze some layers of a learning model, and then you plug some of the new layers to the model. So maybe I missed that on that. So
you did not miss that. It's my problem of not showing too much details here. So actually, we after pre-trained with this task, yes, we keep this pre-trained transformer layers and stack new layers on top of it, and try to predict, for example, function similarity. Let's say if we're doing function similarity, here we have pre-trained model, we indeed stack more layers here to transform the output of the pre-trained model to another embedding and then match their similarity. So, but here, like you said, we did not freeze the trained weights in this pre-trained model. We still let it also gets updated, like fine-tuned when matching similarity, but they will kind of like a bootstrap or gets started from the pre-trained weight parameters. That's how we define this as a transfer learning.
I see. Yeah. Got it.
Thanks for
okay. Yeah, I don't have other questions. I don't see any other question from the audience. So maybe we can end now early. So Megan, I think we can stop recording, and yeah, I think that's. Let me see how to stop it. Record. Megan is recording.
I'll stop sharing.
So are you still there, Megan? Okay. Anyway, so yeah, I think it's a great talk. Yeah, thank you. So one thing we can do is like you can talk with like Song and Leo. I think Leon asked a question. I think he's still here. So I think they are they're all very interested in our work. So I'm actually going to teach a class, so I can talk with them. And if anyone that interests you, people can stay here and talk with you. So I think.
Yeah, that sounds good. Thanks so much. I will stay here for another 20 minutes or
okay. Yeah.
Yeah.
Thank you, Kexin. Yeah.
No problem. Thanks, Inge.
Sure. Yeah. So Leo and Song, I leave to you. You guys can talk with.
That's good. Sure. Hey. So. Yeah, first of all, that was excellent presentation, I thought. I think you presented everything from the ground up very well. It's a complex topic.
Thanks so much. Right. I try to write down my speech, to be honest. Maybe you can also tell that helps me to not making too much grammar mistakes when presenting.
Yeah, I mean, it's certainly not an easy topic to present to, you know, a breadth of audience from all different backgrounds. So yeah, good job.
Yeah, what are you working on now?
So yeah, I'm working on my doctorate as well in a similar sort of field, or actually more or less the same. I was focusing on applying you know, machine learning methods to reverse engineering. So I'm in the process of developing a proposal, some gathering information, etc. But I've recently done some of the similar work using an embedding scheme called instruction2vec, which you referenced with ASM2vec, with some convolutional neural networks for vulnerability classification or identification, I should say, purely on artificial binaries. So this is cool stuff. And you mentioned you had run this against some real CVEs, right? So is that have you made that those results in the paper, or?
Yeah. Well, the results are in the paper. It's just like the firmware is too large, and I no longer maintain the firmware images. So, but yeah, it is. I can point you if you are interested to
Yeah.
how to correct them. Yeah.
That's definitely cool. I can reach out to you with more questions, I guess, after I go through the papers.
Sure. Feel free to reach out to me. And I think what you are doing is also very interesting. I'm also, for now, because I'm just architecture-wise, at the upper layer, I'm using the state-of-the-art transformer architecture without too much modifications. And I think what you are using convolution indeed makes sense for modeling code, because there are just too many repetitions in the code sequence. For example, you have same instructions appear in different places. Those are actually amenable to be modeled by convolution, by applying convolution kernel. Yeah, like similarly on all locations of the code, instead of using transformer, which is too computational heavy. So yeah, I think I would love to learn more about your findings. Yeah, if you have. So.
Yeah, we could definitely talk more, certainly offline. There was some interest in applying attention modules to the architecture that I was using, so you can draw more attention to the actual vulnerable sections of the code, so to speak. It was also interesting seeing that you had these your so-called operational semantics. You're using actual traces, which makes a lot of sense. It was something I was trying to stay away from as much as possible. Just I have a reverse engineering background, and the burden of running something that you're trying to reverse engineer is often pretty heavy. So the more you can stay away from that, the better. But it does make sense. And seeing these microtrace approach is one that I actually had some interest in, and I sort of started to look in that direction. So this is really cool. But
yeah, I also agree with you. It's just like for me, I'm more from the ML side. I just recently transformed my research interest to more program analysis heavy. So yeah, I'm also learning like the key subtasks in reverse engineering that might be helped by machine learning, because in general, I know traditional technique still dominates, or this typical program analysis technique dominates reverse engineering. I'm just trying to identify those neat problems in reverse engineering that might make sense using ML.
I mean, you hit all the major points. I had absolutely no objections.
Yeah.
Cool.
Hi, Kexin. Hi.
Hi, so
yeah,
how are you?
I'm good. How are you?
I'm good.
Yeah. I just have a small question about the macro running you mentioned in the first paper. I noticed that you are like Inji just talked about. Probably you're just doing like data flow analysis instead of control flow. Is that because like you are just doing the micro analysis, like the context non-sensitive, insensitive context like analysis just within a scope of a function? Is that because of this reason, or you have?
Yeah, that can be a very good reason. It is context insensitive because I always execute at the function level, but in the state former, in the second paper, we do log control flow in terms of which static code are executed in this run or not. And then we ask the model to also predict the control flow, like given this trace values, will certain instruction be executed or not? Then the model has to infer some control flow. But during this learning process, we find that essentially, if you are going to predict control flow, it is essentially boils down still to predicting some data flow, like predicting the argument in the comparison instruction, predicting their value, if you can predict their value accurately, you are essentially predicting well the control flow, right? If the value,
yeah,
yeah,
I
the
understand that part. Yeah. So I'm also doing something related to the program analysis. Basically, I'm doing what Indra just mentioned, like analyzing script-based languages like JavaScript, PHP, or Python things. Currently, we developed JavaScript like analyzer. That's why we are asking what analyzer you are using. Yeah, pretty much. I'm planning to do the similar thing. Uses machine learning to predict something like predict the path, which path to go. Like if we have a if statement, we may have two options, like the first one and second one, where to go, which one is the right way to go to reach a specific location. That's what I'm trying to do now. I'm also trying to use something like the transformer, use the self-attention model. I think that's very promising, right? Do you think so? Like use like the transformer to predict the relationship between different variables. Do you think that's something we can try?
Definitely. I think what you are doing is very, very interesting. And what I have tried, especially applying transformer related architecture or this pre-training idea on code, turns out to be honest, always successful. That is surprising, but that is what I have experienced. So that gives me a lot of promises. And also, I think if you look at the recent progress in the industry, that is also the case, right? Although people show that Copilot generate vulnerable code, generate some nonsense code, but in general, it is.
They may leak some information also, like some private code also are trained in.
Oh yes, that's true.
Yeah, some security issues.
Yeah, I think I would not decline. The model might memorize a lot of things instead of really learning semantics. But turns out that memorizing things automatically still saves a lot of effort, engineering effort for program analysis. And what I have, but it is indeed time consuming. I'm using 4 GPUs, and usually this models I pre-trained takes around half months to finish.
Okay.
Yeah, it is like a huge number of binary code and trace values. And turns out that, like you said, transformer is really promising because its architecture is agnostic to any program structure. It assumes any token can connect to any other.
Yeah. That's a self-attention model.
Yeah, self-attention model. And powered by this huge number of training data in pre-training, a transformer really learns like this very complicated dependencies between tokens. So that's why I think that's why it is so successful when applying to many program analysis tasks.
Yeah, great, thanks.
No problem.
Have you considered using something like symbolic execution for your traces?
Right. I think that definitely will improve the quality of the trace. The selling point for my current project is more on this data-driven noisy traces learning, right? So I care more on the cost, like how executing a program the expense of execution can be reduced to some very noisy execution. But if symbolic execution can help us to train on less traces, that will be very cool, I think.
Cool. Okay, well, I'm out of questions, I think.
I appreciate your guys' very long discussion. But I'm gonna call it quits here, I think. But thank you guys so much for everything. It was a really great talk.
Thanks so much for organizing, Megan.
Oh, of course. Yeah, I'm gonna stop recording.